After the complicated release of Llama 4 last month and disappointing almost everyone at Reddit, Meta says there's no point in being creative pre-training LLMs right now. But wait, could they have a point here? And why aren't there more people working with model pre-training? NACO 2025 happened last week, and Mike Lewis, our prolific Meta AI engineer, is this slide on his talk, Pre-Training versus Academic Research. Just by the title, pre-training is seen as something that is different from academic research. Why is it that way? Pre-training is the first step into training a large language model, and it's super expensive. It's so expensive that most researchers don't even think about doing this. There's only one chance to get it right. We're talking about millions, if not billions of dollars went through the sinkhole. So in that sense, academic research is far away from doing the level of pre-training that Meta does. But there's a very important point here. It says no points for creativity. Watch this.
Actually, I think the whole community is very thankful for release of Llama 3, Llama 4. But at the day of the release, at night after release, I was actually looking into the code and I was a little bit disappointed about how you handle actually the long context. It was just, I was expecting like Mamba, something SSM thing going on. But I found just, what you just presented, local context with some global layers. After that, there was some other benchmarks that show that Llama may be not that good as compared to Gemini in terms of handling the long context. And the question is like, do you think that maybe they were like a little bit more creative in terms of how they handle this long context? Maybe they just moved to another architecture, or maybe they just did the data generation, the synthetic data generation right that helped them to handle this context better?
Right, yeah. So, good question. So, firstly, our goal was not to be creative, right? We wanted to use whatever worked best. If we thought Mamba worked better, we would do Mamba. In terms of like the particular Llama 4 release issues, I think, unfortunately, there's an issue where a lot of the third-party providers had bugs in their implementation, which is not their fault, but
Our goal is not to be creative. Our goal is to use whatever works. As he said in his talk as well, we have a big gap into pre-training LLMs right now because we have some people that are working still on training, but that these things don't translate very well to when you go to hundreds of billions to trillions of parameters. From his point of view, I understand that it all makes sense not to be creative. Actual research is all about being creative. And we need that to have our works as researchers accepted at conferences like NACO 2025. And that means risk, because being creative is risky. Not only Meta, but all companies avoid when we are dealing with something that costs hundreds of millions of dollars. You may think, okay, but isn't each company doing things different with their models? As he said, Gemini seems to be better at long contexts. And yes, they are. When we see the technical reports and we see some papers that get released, they are, but not so much in the pre-training part. Pre-training has almost stayed stagnant since GPT-2. Let's take a look at 3 big releases of the past 2 weeks. 5.4 Reasoning Technical Report. This was a work adapting 5.4 to reasoning techniques. 5.4 was already trained at this point. So 5.4 reasoning doesn't really contain pre-training step, right? They are not initializing the model from scratch. We do see in this paper mentions the importance of the selection, filtering of prompt and responses, as well as the critical role of data mixture and training recipe. They just call data-centric pre-training strategies. The only time the word pre-training was ever mentioned in this paper, in this 33-page paper. If we look at the original technical report released last year, there are more mentions to pre-train, but it's mostly about the data that they used, and some of the people are now calling me trainings, which you can understand as, at least what I understand is a new way to do curriculum learning. But most of the works will be focusing on the post-training. If you look at the Quant 3 release report in their website, you will see that there is a section on pre-training. And they even say that the pre-training was twice the number of tokens, approximately 36 trillion tokens, several languages and dialects, and that it consisted of 3 stages, that the pre-training was first done with 3 trillion tokens on a certain context length, and then they improved the data set with more specific data, and then they finalized with long context data. So you're seeing that the actual algorithm of pre-training is not changing a lot. But when you look to the post-training parts, there is a lot of things here. They get the base models, which are the pre-training ones, and then they go to long COT, cold start. There's a reasoning around, there is stage 3, stage 4, several things happening here. But the base pre-training part is just about sorting the data, right? It's all about the curriculum of the data and not much about the algorithm itself on the pre-training part. Not even much about the architecture is even mentioned here. And that's actually which is the most interesting paper that was released, in my opinion, this week. It's the Llama Nemotron Efficient Reasoning Models. This paper doesn't even have pre-training at all because, as the name implies, it starts from a Llama model. And this is something that I've seen called inheritance or inherit tuning. You start from a model or some weights of an original model, and you do continued pre-training. That's actually the word that I use here, continued pre-training with knowledge distillation. But this paper is very interesting because they do talk about how they adapt the original Llama for whatever goals they had. They start by creating inference optimized models. They use this puzzle framework, which I've never heard before, to perform block-wise local distillation and actually remove some of the attention blocks and vary the fully connected layer dimension. They basically do NAT, neural architecture search, is hyperparameterization technique in which you're going to search the initial architecture of your model. And this is usually done before the pre-training step. But in here, they use this with a model that is already trained. They probably were able to surpass DeepSeek R1 with third of the parameters here. And starting from Llama 3, not even Llama 4. So it's a very interesting paper because they basically got a model that was not optimal, at least they was not competing with these other reasoning models. And they adapted it very cheaply. Their post-training steps simply only use 40 billion tokens. Of course, this is a lot still, but when you compare to the pre-training step of WAN3 that used 36 trillion tokens, talk about 1,000 times less. Pre-training is made of 3 pillars. First is deciding an architecture, deciding the hyperparameters. The second one is deciding the data. So we're going to talk about curation and curriculum learning. And the third part is the objective. And the objective has been predicting the next token for 5 years right now? Maybe. That's at least what the state-of-the-art models have been doing. And they haven't changed that for a long time, the next token prediction, which has been stayed the same for a while now. Because in essence, the way that people have been thinking about pre-training is a lot of data and a lot of compute. This way of thinking, I think it really makes pre-training seem very expensive. Not even NVIDIA decides to pre-train their latest model, right? So everyone seems to be focusing on the cheaper parts, like model post-training techniques, which seem to be very effective. And many more people are able to do experiments at that level. And that's exactly the point of Meta's engineer. Their goal is not to revolutionize pre-training. That's what the community is for. That's what we are for, researchers. And that's why I think we need new ideas in pre-training research, even if they're risky, even if they are hard. Here, when you talk about these things, we usually hear about Mamba and other model architectures, but there is more than just model architecture, people. Byte latent transformer, patches scale better than tokens. So this is the idea of trying to do a tokenizer-free model, which they show can scale even better than tokenized models. If you don't know, every model, the first layer is what you call an embedding layer. It's basically a dictionary that tells what each word should be represented as a vector in high-dimensional space. So think that every word that you know, or at least most of the words that you know, would have a vector representation. And this works well because you're going to have a lot of words. So you're going to have a lot of vectors. So there's a lot of diversity and variety. But when we go to byte level, we're saying that it's a character. Every character is going to be represented as a vector. There are not enough tokens to represent all of human knowledge in this case. When you talk about words, tokens, we can easily have 200,000 different tokens. We can easily have 200,000 different words. Think of more or less like that. But when you have characters, that's very complicated. If the geometry is a proxy of your diversity, of the quality of the knowledge you have, you can put a lot of information just in the tokens itself. But characters, how many characters we have in English? If you count numbers, maybe 50 or something. And that's why it's very hard to do this. It's very hard to do byte level models. Why should we use these bytes if they are so complicated? Why not keep using tokens? And the problem is that tokens, they are defined by a compression algorithm. There is a fixed algorithm. Whereas we want the model to be able to learn anything. So they get the model to learn how to split the words, and they use. So you can see here, there are several ways that you could split the words in this sentence, right? Maybe there are repeatable parts, or maybe for the model, splitting by spaces that would make sense. Maybe splitting by groups of them makes more sense. And the promise that they show is that for fixed compute, they seem to be able to reach a scaling law that is preferable than tokens. And that's the actual promise of this. But that's not only the new idea. You also have things like Dream 7B. And they are using something that is diffusion reasoning model here. But to be fair, this is not diffusion as in image generation. This diffusion here is the idea that the model could generate the words in any order that it prefers. So instead of just generating one token after the other based on the previous ones, what if you just give me a budget? Let's say I allow you to generate 100 tokens, and I will do my best. And this best does not involve one after the other. And they got pretty good results with their model. And when we talk about diffusion models, all of the previous ones were very bad. So it's very interesting to now be seeing something that worked well. Again, this idea of inheritance starting from a model that was already pre-trained. So you could see this more as of a continued pre-training step than actually pre-training from the ground up. So Dream 7B was initialized with weights from Quen 2.57 billion. And they show that the initialization is much better than training from scratch. It converges to a better level. Even though the task was completely different. Before, the model only focused on predicting the next token. And now the model is trying to predict any token in the future. It's a different task. And it's nice to see these people trying it, because I think that one of the main limitations that we have in pre-training right now is this idea of just predicting next token. What if we predicted 2 tokens? Wouldn't that be amazing? So that's what I have for you this week. I hope you enjoyed this video. Leave a like if you liked, and I see you in the next one.